approximate free radiation. Okay, so what we assume, and this is here now very important, is we assume an inviscid fluid. The inviscid fluid means that we will have no shear forces being modeled in the fluid, because we assume that the viscosity is so small. The fluid particles, they move forward and backward in this sense, and the driving force is the pressure. So this is the important physical quantity, and due to the fact that we have an inviscid fluid, which also means that we neglect viscosity. So I perhaps should also write here, that means that we neglect viscosity, we have no shear forces, and that means that we just model longitudinal waves. Yeah. When you also take into account that it could be for some cases, even for acoustics, that you have to take into account viscosity, then we also model the shearing of the fluid, and then you also have clearly transversal waves, also shear waves. In our case, we just have longitudinal waves, and the most important equation here is the relation you have between the wavelengths, which is a periodicity in space, and the frequency we have within the wave propagation or the time period, and that is given by the speed of sound. And so we see, since the speed of sound we can assume for most cases to be constant, we can then see that the higher our frequency is, the smaller the wavelengths. And this is a very important impact for us, because we have to do space and time discretization. So our main parameter for the space discretization will be the wavelengths. We have to resolve the wavelengths spatially, and the main quantity for the time discretization will be, as you already had for other physical systems, the maximum frequency within the excitation. Okay, so if we now look at this sense, as I have told you, so you have, for example, in this sense, somewhere a lot of microphones at a fixed time, and you record this at this time, and now we show here the dependency of the pressure, of the acoustic pressure over position. Then perhaps you get such a sine or cosine function, and the main quantity here is this wavelength. So we have a kind of a periodicity in space, and clearly we also have this periodicity in time, and that is the main property of each wave, also for electromagnetic waves or any mechanical waves in solids, that we have a periodicity in space described by the wavelengths, and a periodicity in time described by the time period. And that is also shown here. For example, we have a loudspeaker. You see here from a simulation how the waves propagate away from the loudspeaker. And if you just take out one monitoring point, virtual microphone as we also call it, then you will get what is shown here. We have at a fixed position the pressure over the time, and perhaps you see that we have such a harmonic function, and clearly t, the time period, is 1 over the frequency. And actually the frequency you see here is the frequency of the electrical signal, of the electrical audio signal you put on in the voice coil within the loudspeaker. On the other hand, if you look at a fixed time and you take a lot of these monitoring points, for example, along the x-axis, you get a very similar behavior. Perhaps you will also see somehow the decay of the amplitude. Anyway, we have such a periodicity now in space according to our wavelengths. And you see how different the values are if you are in air, where the standard speed of sound is 343, so mainly you just remember 340 meters per second. In water, it is, as you see, almost 5 times as large. On the other hand, also a big difference is seen in the density. That is also very important when you have a coupling to mechanical structures. It's a big difference if your vibrating membrane is vibrating in air or it is vibrating in water, where you have a difference, a multiplication factor of about 1,000 between the densities in air and the density in water. And that clearly has a strong impact, as you can see here on the wavelengths. And if we look here at some fixed values, so if we are in air, then we have quite large wavelengths at 100 Hertz, which is 3.43 meters. So as you know, our transformers are here according to 50 Hertz. Now the electromagnetic forces double these frequencies because you have this nonlinearity. The electromagnetic force is nonlinear, which means the main frequency at which the coils are vibrating of your transformer are at 100 Hertz, and these vibrations are then transported over the oil to the tank, and the tank then radiates acoustic waves at about 100 Hertz, and you see how large the wavelength is. If you go to 1 kilohertz, then clearly we have about 0.3 meters. On the other hand, if you look at water, we have, since we have a factor in between here concerning shown here, which is almost a factor of 5. We have 50 meters at 100 Hertz. We have 1.5 meters at 1000 Hertz. Now perhaps you also know that in non-destructive testing, which is in short written as this, so non-destructive testing is using, as we call it, ultrasound, which we cannot hear. So ultrasound is in the range of about 100 kilohertz going up to about 10 megahertz. Now, if you want to use non-destructive testing by ultrasound, well, we should be at least somewhere in the millimeter range, and then it is clear that the frequencies you are using there is in the range of megahertz. Yeah? If you have 1 megahertz, if you look here, then this value would be not 1.5 meter, it is 1.5 millimeter. And the same is also for medical ultrasound imaging. So we are there also in the megahertz in order to resolve the different tissues within a human body, as you know, since we are quite similar as water concerning the properties. Okay, when we now restrict ourselves as a medium to air, then we have this frequency range concerning the hearing of humans, which is starting at about 16 to 20 Hertz, and the highest frequency we realize with our ears is somehow between 16 and 20 kilohertz. So you see that is quite a large range, and it clearly shows that we need fluctuating pressures in order to perceive this with our human ears. Okay, and we need clearly pressure amplitude changes, otherwise we cannot hear it. Now the threshold is quite interesting and is, as you can see, quite low. So we can even hear such small amplitudes of 20 micropascal by our human ears, and it is dependent on the frequency. Actually, this 20 micropascal is at 1 kilohertz is the average threshold of hearing, and clearly you will have strong pain if the amplitude is somehow about 200 pascal. Anyway, that is nothing, because as you perhaps know, the ambient density, ambient pressure, clearly I wanted to write there, the ambient pressure, which we will call here with P0, is 10 to the power of 5 Pascal. So we see actually these amplitudes which we receive, or the amplitudes you have within the sound, is quite small. Now, loudness changes is also of interest. So you will perceive it equal if we have a change from a pressure. Now this is not the P0, it is any pressure to double the pressure, or it is 5 times such a value to 10 times. So you see it is just the relative factor is of importance. Now if you record with a microphone the acoustic pressure, now the question is, what is the quantity we put there? And that is the so-called quantity, the sound pressure level. So this is also called we will see shortly, in short, SPL, and it is called sound pressure level. And as you can see, first of all, from your time signal, you compute out the RMS pressure and you normalize this to our threshold value, which is 20 micropascal. Take the logarithm and this 20 times. And this is then called the sound pressure level. So that means also when you have a lot of different frequencies, as for example, now you can hear when I'm speaking, then there are different frequencies in my human voice. And this means you also go over all these frequencies because the RMS value includes all them, and you get out one scalar quantity. Now, how large are these values? If we are speaking, as you can see here, what is always important that you also define the distance. Yeah. So very simple speaking, we have a distance law, so that when waves are propagating, then the amplitude decays with 1 over distance. That is exactly for a spherical wave, but for a lot of other scenarios, when you have a vibrating motor or whatever, and you are at some distance, you can model this like a point source, and then you have this distance. So whenever we see how loud any device is, and you get the value of the sound pressure level, you should also get there the information about the distance. So you see it is 60 dB at 5 meter. If we are looking at the car, it is about 80 dB. Motorbikes is about this. What is missing here is a disco. So when you go to a disco, you will have here also at about 5 meter almost. It depends clearly, but in a real disco, you have almost 120 dB. And especially for low frequencies, so the bass we have there, you even can feel it on your body, that also your body starts to vibrate. So there is also, as we call it, a sound pressure excitation on your body. And clearly for a jet, you see how large already this is. On the other hand, we know that the sound is a byproduct of the flow, and for any flow, these are very small quantities, and that will also allow us to do a perturbation ansatz to get out from the compressible flow equation, the wave equation. Okay, further on, what is important is that very often we do not look at a frequency spectrum of the recorded signal, so which means you have a recorded signal of the microphone, the pressure is a function of time, and transform it in the frequency domain, but we filter this signal to have one using an octave filter, for example, or a 1/3 octave filter, and for this we also define here the middle frequencies between a lower frequency and the upper frequency, which you compute by the square root of the multiplication of these two. And then according to a 1/3 octave filter, so which is a Terz in German, means that we have here these simple relations by this factor A, which is the third square root of 2. And you see this as follows. So this would be a simple filter where always the lower and the upper frequency is defined in the norm in over the human audible frequency range, and then you apply such a filter to your signals, and within this frequency band you just sum up your sound pressure level. Okay, and that you have for different middle frequencies which are normed, as I have told you, and then for each of these middle frequencies you get one value out of your spectrum. Okay, now, as I have told you, actually when you solve the compressible flow equation, you also solve for acoustic waves. The question is always just what is flow and what is acoustics. Anyway, we will start here at the conservation equation of mass and momentum. So what we have here is the conservation equation of mass, where rho is the density and v is the fluid velocity. So the velocity of the particles being driven, for example, by a pressure gradient. And we have a second equation, and in the second equation we have an additional quantity which is here given by the pressure, and that is the viscous tensor. So this viscous tensor, it's again a 3×3 matrix, models the viscosity of the fluid, and which in our case will be neglected because we assume that the viscosity in the mediums we are considering, and mainly we are considering air and water, is so small that we can neglect it. Okay, and due to this fact that we neglect this, so when we cancel this out, it automatically follows that we just can have longitudinal waves. Because waves, I should write here, not force, because we have then no shear forces. Okay, so we just neglect this, and we call this then the property to have an inviscid fluid. Okay, now what we do, and that is very often used in physics, when we have a superposition of a mean quantity which is very large compared to a fluctuating quantity, we can do this simple ansatz of a superposition as we see here for the density. So we assume to have a mean density which is very large compared to a fluctuating density. So this here is very large compared, let's say, the absolute value, because the fluctuating density has plus and minus values. Therefore, I put here the absolute value. And in such a case, we really decompose it by a sum of the large quantity, which is the ambient quantity, and the small fluctuating quantity. And the same we do for the pressure, and the same you do for the velocity. Now we assume that we have wave propagation without any background flow, so we set V0 just to 0. And now such a perturbation ansatz, what we have here, you just plug in the equation we have just seen before, the conservation of mass and momentum. And then it is clear that we analyze this equation and look which terms popping up we can cancel out, and we will just remain with linear terms in order to come up to a linear wave equation. So that means the following now, we take this ansatz as shown here. This is set to 0, and we just put it in here in our two equations. The first equation is the conservation of mass, and the second equation is the conservation of momentum. And what we also assume that the mean density and the mean pressure are constant, and it is important that they are constant in space and time. Yeah? It could be that they change over space, especially density can change over space, even in air. If you have some regions of hot air, for example, then you will have, for example, a gradient in the density. Then we have to be very carefully when we do space derivatives. Then clearly a space derivative of the density, of the mean density, will not be 0. However, we assume that we have now somewhere, we are sitting somewhere in a room, we have no background flow, and we can assume that the density, the mean density and mean pressure is constant. Okay, so this was the first step. We just plug it in. Yeah, and then clearly you can look at all those things. For example, if you look at the first term here, then you can say this is nothing else as the partial derivative of the acoustic density with respect to time, because the partial derivative of the mean density with respect to time is just 0. We assume it is constant in space and time. And the red ones, what you see here, this is a bilinear term. So it is the multiplication of two perturbed quantities, as we call it, the acoustic particle velocity, as we call it. We just have a special name in German. In German, we call it we call it not Partikelgeschwindigkeit, but we call it, who knows it? I have just forgotten it. How can this happen? Schnelle, yes, very strange word. Anyway, you call it Schnelle in German. So just here we have a special word. Okay, and this would be a bilinear term is already a nonlinear term in this sense. So these red terms is also popping up here in the conservation of momentum. And especially you see it here, which is totally nonlinear. Even if we just multiply it with the mean density, we have here a multiplication of these perturbed quantities. So in this sense, all these red terms we will just neglect. Here we can also say that this term here is equal to 0 because we assume a constant ambient pressure. Okay, so assuming this constant ambient density and pressure and just neglecting all these bilinear and nonlinear terms, we end up in this case now in linearized mass equation already for the acoustic quantities, the acoustic density and the acoustic particle velocity, and on the other hand, the conservation of momentum in a linearized form for the acoustic particle velocity and the acoustic pressure. Okay, so these are the linearized conservation equations for, and importantly, for linear acoustics. So we assume that the acoustic quantities are small. We also have shock waves, for example, where this assumption would be not correct, but for a lot of waves, if it is coming from music when we are speaking, or it comes from, and which is annoying, from motors or any other technical devices, we can assume that for most cases we can do this approximation. Okay, now in this sense, we assume a thermodynamic state which is adiabatic. So we have a adiabatic state where we get this very simple relation between pressure and density already written with the acoustic pressure PA and acoustic density rho A over the speed of sound V, which means in the conservation of mass, which is the first equation here, we can now substitute the density by the acoustic pressure. Yeah, and if we are looking at this, then you see that we could do some mathematical operations in order to come up to a single equation for the acoustic pressure, since the acoustic pressure is the main physical quantity for us. And you see that we have here, in this sense, this term where we have the divergence of the particle velocity, and here we have a time derivative. Now, we can see that when we do the following operations, we do a time derivative on this equation here, then you have space and time derivative on this term here. Now here we just have a time derivative. Now let's apply here also a spatial derivative, meaning we just apply the divergence on this equation. Then we will also have here space and time derivative on this term. Since the density is constant, now you see how important it is. If it is not the case, then you have to do some different operations and take into account that the space derivative of the density, the mean density, is not zero. But in our case, you see that we get now here the same term as here. And when we subtract the two equations, we come up, as you see here, for a term of a second time derivative, since on this first time derivative, we perform a further time derivative. Here we have the gradient and apply the divergence, so we will have here the Laplacian. Okay, so what we see here is that we get out then our standard wave equation, and this is the very important property you always have for wave equation, in this sense that we have a second time derivative which is equal just by some scaling. It is 1 over the speed of sound squared, and here the second space derivative. And that also gives you this periodicity in space and time, and that is typically for each wave equation, if it is an electromagnetic wave, an acoustic wave, any mechanical wave in a solid, for example. Okay. Now, let's have a little bit more details concerning the thermodynamic state, since we can express in a thermodynamic equilibrium that the pressure is just a function of two state variables, as shown here, which is here the density and the entropy. Then we see that the total differential is nothing else as the partial derivative of the pressure with respect to the density at constant entropy increment d rho plus the partial derivative of the pressure with respect to the entropy at constant. And this is a mistake we have here. Sorry, that should be not the pressure, that is a constant density clearly, and the increment ds of the entropy. Now, the definition of sound can be shown that this is the direct relation between a pressure change and the density change. And as you can see here, it is exactly this partial derivative of any pressure state in a medium, in a fluid, for example, with respect to the density at constant entropy. And what we assume is that we have this adiabatic state, which is also reversible, which means that there is no change of the entropy. So that means we just have this relation here, and that gives us then the relation between the perturbed quantities, which are the acoustic pressure and the acoustic density, via the speed of sound. Okay, what is very interesting is when you look here at these quantities here, we should get out that at least this term C here, at this stage, we cannot exactly say that it is the speed of sound, but we can say that it has the quantity, the unit of meters per second. So now let's look. The pressure, as we know, is Pascal. Pascal is Newton per square meter. Now, Newton can be also written. Newton is the unit of a force. Let's say the force is our acceleration force. So it is the mass, which is kilogram, and the acceleration is meter per second. So it is here meter squared, second squared. And then we have the density, where we know the density is kilogram over cubic meter. Now, if we relate these two here, we have to divide. Then you see the kilogram is just cancelled out. And what we get out is meter squared over second squared. And now if you take the square root, you see at least the unit is the unit of a velocity. And in a precise investigation, you then can also demonstrate that the speed of your wave is exactly this velocity, which we call the speed of sound. If you are in an idle gas, then you can also express this speed of sound by the ambient pressure, the ambient density, and this factor kappa, which is also called the adiabatic exponent, and which is the specific heat ratio. And you see that you can also compute it out by this formula, by expressing ambient pressure and density over the gas constant and the temperature. And that is important. So this is the temperature. So you see that the speed of sound is a function of the temperature, and it depends somehow by the square root of the temperature. So you see, the higher the temperature, the higher also the speed of sound. If you are in a liquid, the standard form is that you look up for your liquid what is the adiabatic bulk modulus and what is the density. And again, you just divide K by the density and take the square root and get the speed of sound in a liquid like water, where we have the speed of sound approximately 1,400 to 1,500 meter per second. Okay, so now let's also have some investigation into the property of the acoustic field. So perhaps you remember that this was the linearized equation, the linearized momentum and what we do here, we apply the curl operator. You know, the curl of a physical field gives you the vorticity. Now the curl of a gradient is always zero. So what remains if we exchange time and space derivative, that the curl of our particle velocity and taking the time derivative is zero, because the linearized equation which we have here was mean density time derivative of particle velocity plus gradient of the acoustic pressure equal zero. Okay, and so you see at the end, you can also integrate this over time. You see that the curl of the particle velocity is then somehow a constant, but we are not interested in constant. In order to hear sound, we need time changing physical quantities, which at the end means we can define that the acoustic particle velocity is irrotational, which means we have an irrotational physical field. So very similar to the electrostatic electric field. And as you know, we always can introduce then a scalar potential to express such a vector field, such a irrotational vector field. And we call this scalar potential the acoustic scalar potential. Now, if we substitute this back, now I perhaps rewrite it here, where we have mean density time derivative of the acoustic particle velocity plus the gradient of the acoustic pressure is equal to zero. Now we substitute this in, and we do the substitution, we get out this equation here, which we can rewrite here by taking again all the terms within the gradient operator. Now you also see how important it is for this kind of modeling of acoustic waves that the mean density is constant. So you have the time derivative of the acoustic scalar potential minus the acoustic pressure, and that has to be zero. And again, here you can integrate over space, so then the right-hand side would be a constant, but constants are not of interest for acoustic fields. We cannot hear constants. We also need always alternating quantities, which means we can directly express the acoustic pressure as the time derivative of this scalar potential. And in some cases, it really makes sense to use this acoustic scalar potential, although in this way, as we have seen, we also have our wave equation as a function of the acoustic pressure, which is also a scalar, and that will be the main partial differential equation we are solving to get acoustic fields. Okay, now in this case, you can also then look up our equation, and you will see that when we have this relation, I just write it here, that the acoustic pressure is equal to the mean density and time derivative of the scalar potential. And as you know, we have introduced it by expressing the acoustic particle velocity by minus the gradient of the scalar potential. And that we have obtained out of our conservation of momentum. Now we also have, in addition, the conservation of mass, which was 1 over the speed of sound squared, time derivative of the acoustic pressure, plus the divergence of the mean density. I have forgotten here. The divergence of the acoustic particle velocity is equal to 0. So you see, we just put in here the relation, then we get the Laplacian of the acoustic scalar potential, and we put in this relation here. Then we have the second time derivative of the scalar potential, and as you can see here, the mean density just cancels out. That we also have the same wave equation for the acoustic scalar potential as we had for the acoustic pressure. So they solve the same partial differential equations. Okay, now concerning our boundary conditions. So a main boundary condition is the following as shown here, that as you know, we have, and that I should rewrite here, we have this linearized conservation of momentum. And at the boundary, when to get at the boundary, we take the scalar product with the normal vector, and then you know that the scalar product, not with the gradient here, so I have to put this away, and we take here and project it in normal direction on the surface, then this is nothing else as the normal derivative. And we know the normal derivative of the physical quantities gives us the flux, or speaking mathematically, the Neumann boundary condition. And as you can see here, that this is, on the other hand, according to this relation, it can be expressed by this term. And now you have a very important continuity equation, or I think this, I want to name it interface condition, which we will need later on, the coupling to mechanics. So when we have a interface to solid mechanics, then there you have that the normal component of the mechanical velocity has to meet the normal component of the acoustic particle velocity. And this is a very important interface condition between acoustics and solid mechanics. And now if you put this in, what you actually see is that we can express VA by Vm, which is the mechanical surface velocity of a vibrating mechanical structure, let's say the membrane of the loudspeaker. And since we have the time derivative here, you see that actually what is driving the acoustic waves from vibrating mechanical structures is the acceleration. The n means just the normal component of the acceleration. The tangential component cannot excite any acoustic waves because we model here a non-viscous fluid. If we would take into account the viscosity, then you can also have a tangential component generating shear waves propagating into the fluid domain away from the solid vibrating body. But we have concentrated here on non-viscous fluids. Okay, and you see that instead of this definition, we can define this also as shown here by the acoustic scalar potential. And for the acoustic scalar potential, the Neumann boundary condition is really the normal vibration velocity of the mechanical body. So you see that is the difference if you have and model your acoustic wave by the acoustic pressure or by this acoustic scalar potential. Yeah, then clearly we can have any homogeneous boundary condition, which would mean that the normal derivative, yeah, so that would mean the normal derivative of the acoustic pressure is equal to 0. But I think the better explanation we see here, because out of this equation, dB a dn, we see that we have here the following. I just put it in, that the time derivative of the normal component of the acoustic particle velocity, which we can also rewrite as the normal component of the mechanical velocity. It means that you have a wall which is not vibrating, and then you can model this in this sense by this homogeneous Neumann boundary condition, and we call this a sound hard wall. Okay, and this was also here this last one I should not forget, but that we have discussed here was exactly this interface condition between mechanics. I just have named V here, but I like to have more this index M for mechanics. So at the surface of the mechanical body, the normal component of the vibration velocity has to meet the normal component of the particle velocity. On the other hand, we can also have clearly Dirichlet boundary conditions. And for the Dirichlet boundary condition, you directly prescribe, for example, here the acoustic pressure, if you know it. That would be a soft wall boundary condition, or you directly prescribe here your acoustic potential in an inhomogeneous way, or in a homogeneous way. Then if this pressure is equal to 0, you would call this a sound soft wall. Okay, so we have this boundary condition. Clearly what is left is when we have free radiation, and this is something we will also discuss, how to model at your limiting computational domain a free radiation, so that when the waves are impinging this boundary, that they are not numerically reflected. Okay, so in order to come up to our weak formulation, it is here in this sense quite easy. We have already our partial differential equation. What we clearly now introduce is a test function, again with the property that the test function is 0 on a Dirichlet boundary, where we already know the acoustic pressure. We multiply our partial differential equation with this test function, integrate over the whole computational domain, apply the divergence theorem, which means that the multiplication between P prime and the Laplacian of the acoustic pressure, we do there an integration by parts. Yeah, and then incorporate here, because by this integration by parts you get also a surface integral, and in the surface integral we could then incorporate any Neumann boundary condition. That will be very important if this surface is an interface to a solid body, where we then can get the coupling between mechanics and acoustics. In our case, let's assume now the following. We have multiplied our partial differential equation by P prime, and we integrate here over the whole computational domain. Now we apply here the trick with the divergence theorem, or simply speaking, you are doing an integration by parts, which means we get this new volume integral, where we also have now the gradient on the test function. And in addition, we get this surface integral, where this term, as you know, we can also rewrite as the normal derivative of the acoustic pressure, and where we can incorporate any inhomogeneous Neumann boundary condition. And the other part of the surface just cancels out, because we know for the test function, we set this test function to 0 on any directly boundary. Okay, which means at the end, for example, when we incorporate here a Neumann boundary condition according to some coupling to structural mechanics, where we have here the mechanical acceleration on the surface of the solid body in normal direction, then this is more or less our driving term. It's the right-hand side term which excites our waves. On the other hand, when we do this for the acoustic scalar potential, this term here would look like this. So you see in this part, the normal velocity, vibrating velocity enters. Here again, I perhaps highlight this with red. It is the acceleration, and here it is the velocity. However, it is physically fully correct, because we have to consider that we have the following relation, that the acoustic pressure is equal to mean density and the time derivative of the acoustic scalar potential, which means when you get and would substitute this, then you would also get out here the acceleration part. So this is the important thing to be remembered in this sense. So it is everything physically correct. If you do the simulation with the acoustic pressure, you directly get out the acoustic pressure. Or if you do the simulation with the scalar acoustic potential, I see there is a mistake, that should be here at A. Then at the end, you get the solution within your computational domain for the scalar acoustic potential, and you have to take a time derivative on it to get out the acoustic pressure. Okay, now let's cope this very important challenge, which is the part of the open domain, which we also call it. So we have somewhere a computational domain, as shown here, and you have a vibrating body. You know the surface velocity or acceleration, so we just compute in omega and solve our partial differential equation. But the big challenge is what to do at the limiting domain surface here of your computational domain. Since the impinging waves here, they would be numerically reflected when you apply their homogeneous Neumann or Dirichlet boundary condition. So we have to do something on this computational boundary in order that the impinging waves are not reflected, and you model really free radiation, if this is the job you have to do. And there are two main approaches. We will just discuss one approach. The second is more involved, but it is also more effectively and will be discussed in a follow-up course we have in the summer semester. So one of the main approaches is to use so-called absorbing boundary conditions, and the other approach is the so-called perfectly matched layer, which is somehow easily to be explained to students coming from electrical engineering. We know the matching within electric circuits, and here the matching also means quite the same. Actually, a perfectly matched layer technique means that we put here some additional domain here, which we call here a damping domain. And now you can construct your perfectly matched layer in this sense that at the interface, which is here coming from the computational propagation domain, entering the damping domain, we don't want to have any reflections. And when the waves are within this damping domain, we try to effectively damp out the wave. And so if they are impinging at this outer boundary now of the damping domain, they will be reflected, but again strongly damped when they travel back. So the part of waves which have not been damped out and entering again our propagation domain should be so small that it can't be neglected. And so this is the main properties you need from such a method called perfectly matched layer, that you have the perfectly matching, you have no reflections at the interface between your computational propagation domain and this damping domain. So the damping domain is some pictures, what you get out there, you just throw away. It's not of interest because you actually damp out the radiated waves within this small region surrounding your computational domain itself. Okay, so when we use standard finite elements, we don't need some special elements. We can use the standard finite element, what we also have used for our other physical systems. Then we come up to a system of ordinary differential equations as shown here, where we have a mass matrix which is multiplied by the second time derivative of our unknowns. Let's say the unknowns are all the acoustic pressures within the finite element nodes, plus you get out a kind of a stiffness matrix multiplied by the acoustic pressure is equal somehow to the right-hand side, which could be any physical sources in the domain you model or are due to some boundary conditions as we have just discussed. Okay, the mass matrix is again such a matrix where we have the basis functions and they are just multiplied by each other, and you see as describing your medium, it is the speed of sound squared, which enters here the mass matrix. The stiffness matrix, as we know, we don't have there in our Laplacian term in the partial differential equation any material parameter, and we have there to take the gradient of the basis functions and then the scalar product between them. And as a forcing vector, this vector f for all the values you have in the region or on the boundary, for example, here modeled as a boundary where we know here, for example, this value g as the mean density and the mechanical acceleration of the surface in normal direction, and that gives you at the end this forcing vector. Okay, so that also means we have to perform a time discretization in order to come up to an algebraic system of equation. We have to solve for each time step, and then we also have to think over how to do this time discretization. On the other hand, we also clearly can do a harmonic analysis. It's clear, we know that this part in a harmonic analysis will give us the complex unit times omega squared. So we should write it in this sense, which we know is just minus omega squared. And then, as you can see here, that in this special case, we do not get a complex system matrix. It's still a real matrix because we have not modeled any damping of the waves propagating within the computational domain, but that is almost a standard if the distances of the traveling of the waves are not so large, you don't consider the damping of the air. Okay, so this would be a harmonic analysis, which is done very often, especially in acoustics. We mostly even if you do a time computation at the end, you transform it to the frequency domain, at least at some monitoring points, to see how the frequency spectra is looking like. Clearly, we also can do a eigenvalue analysis in order to get the natural frequencies. We also call it the resonance frequencies of our computational domain, and also to see the modes very similar as we have the modes within a mechanical computation. Yeah, and clearly we can do a transient analysis, and for the transient analysis, since it is very similar as we have in computational mechanics, there for the time discretization you also use the standard Newmark scheme we have discussed within computational mechanics. A static analysis clearly has no relevance. It makes no sense because what you compute out there we could not hear, as you know, so static analysis makes no sense for acoustic fields. Acoustic fields are always fields depending and therefore changing in time. Okay, and as I have told you, mostly if it is straightforward, you solve the wave equation with the acoustic pressure as the unknown. It's more or less the standard. In a post-processing, you then can also derive the acoustic particle velocity. Sometimes we use a potential formulation, especially in the coupling to structural mechanics that we will discuss next time. And when you have the acoustic scalar potential in the post-processing, it's easy to derive the acoustic particle velocity as well as the acoustic pressure, which clearly is the main physical quantity we are interested in. Okay, so what are some further interesting quantities we want to compute? Especially then in practice, it is something like the acoustic intensity. Intensity, you will see in more or less all physical fields, is somehow a relation between the primary quantities, in our case, the acoustic pressure and the acoustic particle velocity. The intensity is a vector. And when you get any values of the intensity, mainly it is again that you compute the out of the density, out of the intensity, you compute the mean value, and then this mean value is shown here. You also normalize it to the reference value, which is based on the threshold of hearing, so this 20 micropascal, and here you just take 10 times the logarithm, clearly because this is already a power quantity. The intensity is a very interesting quantity also to visualize. It is a vector quantity, so you can also see somehow the energy flow by looking at visualizations of the intensity. For a lot of practical application, perhaps it's the most important quantity is the acoustic power, because if you build a new technical device, it's also important and it's necessary that you also do the computation, or mostly you do also and evaluate it experimentally to know what is the radiated acoustic power. And that is, as you can see from intensity, which is watt per square meter, you have to integrate over the surface of your device. And as you see, you integrate over the surface, but project this intensity in normal direction, where n is the normal vector of the surface. And again, as you can see here, you compute out an averaged value, and then you can also give the acoustic power as a within this part in dB. A last quantity, which is perhaps also interesting, is the acoustic impedance, which is very similar to electrical impedances. As we know, it is voltage over the current. So you see that the potential quantity, which is in electrical engineering, the voltage is here the acoustic pressure, and the flow quantity, the electric current, is in acoustic the particle velocity. And since it is a vector, we always have to project it in normal direction. Here you see also these reference values, and the reference values are according to the reference value of the 20 micropascal. And then it is important how to get the reference value for the intensity and simply the power. It's clear. The acoustic particle velocity as a reference value is computed out by the mean density, speed of sound, and up to -1 to be clearly correct, and the acoustic reference value. And that is given because for a plane wave, means we have just one component for the acoustic particle velocity. That is, for example, within a pipe of a small diameter, then just you have propagating plane waves. The acoustic impedance is then acoustic pressure over the acoustic particle velocity, and this is just mean density speed of sound. So this is normalized as you would have plane waves, and for this here your reference surface is just 1 square meter. And so if you put in mean density, speed of sound, and so on, you will see that we get up this reference value here, 10 to the power of -12 watt per square meter for the intensity reference value, and that value then according to 1 square meter for the acoustic power reference value.